Deep inside our star, hydrogen atoms fuse under immense pressure. This core operates at 15.7 million Kelvin, acting as an engine driven by mass-energy equivalence, where tiny amounts of mass convert into the energy required to sustain the star, as dictated by the equation E equals mc squared. This continuous nuclear detonation creates a powerful outward force. Without a counteracting pressure, the star would blow itself apart. Instead, it is contained by its own massive gravity. This mechanical balance between explosive outward energy and crushing inward weight is a state known as hydrostatic equilibrium. In this state, the inward pull of gravity is perfectly matched by the outward pointing gradients of internal pressure, maintaining the star's stability. Despite this immense energy generation, we cannot observe the stellar engine directly. Optical telescopes only capture photons emitted from the outermost shell, the photosphere. The core itself remains unobservable via traditional light-based astronomy. Because we are blocked by this opaque outer layer, understanding the mechanical and chemical reality of the deep star requires us to bypass optical physics. In the inner 70% of the Sun, a region known as the radiative zone, energy transport is driven by radiative diffusion. Here, the plasma is so dense that a photon cannot travel in a straight line. On average, a photon moves just 2 centimeters before it collides with an electron and is scattered in a random direction. This creates a trajectory known as a random walk, or Brownian motion. Because the photon is constantly redirected, the energy generated by core fusion is delayed. It takes an average of 170,000 years for a single photon to reach the Sun's surface. A 170,000-year delay makes optical information useless for understanding the Sun's current state. To test modern astrophysical models, researchers require precise, real-time diagnostic data from the core. Optical signals are too slow to serve as a diagnostic tool for the deep interior. To peer inside the stellar engine, astrophysics had to find an entirely different signal. The first alternative probe relies on sound rather than light. This field is called helioseismology, operating using ground-based observatories and specialized solar telescopes. The Sun acts as a massive resonant cavity. Near the surface, violent convective turbulence acts like a continuous physical drumbeat, driving and damping sound waves throughout the plasma. These sound waves are classified as pressure modes, or P modes. The restoring force that propagates them through the solar fluid is internal pressure. As P modes dive, their wavelength increases. Refraction depth is dictated by the speed of sound, gamma 1 times pressure over density. Deeper inside, rising density and pressure force the sound speed to increase, smoothly bending the waves back toward the surface. By measuring the Doppler shifts of the solar surface as it vibrates, researchers solve an inverse problem. They use the surface data to calculate the exact sound speeds at specific depths inside the star. These complex vibrations are categorized mathematically using spherical harmonics. Each resonant oscillation mode is defined by specific quantum numbers, mapping the exact geometric pattern of the waves as they ripple across the solar surface. Mapping internal sound speeds allowed astronomers to identify distinct structural shifts within the star, leading to the discovery of a boundary layer called the tachocline. The tachocline is a sharp shear layer. It marks the boundary separating the rigidly rotating radiative zone in the deep interior from the differentially rotating convective envelope near the surface. Acoustic waves map the fluid dynamics and physical boundaries of the Sun. However, sound cannot directly verify the specific nuclear chemistry occurring in the core. To complete the solar picture, researchers still needed a way to observe the fusion reactions themselves and confirm the theoretical models of stellar nucleosynthesis. That confirmation comes from neutrinos, a direct byproduct of nuclear fusion. Neutrinos possess near-zero mass and no electric charge. Escaping without interaction, they exit the Sun in perfectly straight lines, passing through dense layers completely unimpeded. The primary fusion pathway producing these particles is the proton-proton, or PP chain. This reaction sequence dominates energy production at the Sun's core temperature of 15.7 million Kelvin. There is also a secondary pathway for stellar fusion known as the CNO, or carbon-nitrogen-oxygen catalytic cycle. Comparing both pathways reveals exactly where electron neutrinos are released. Unlike the pp chain, the CNO cycle is catalytic. Carbon, nitrogen, and oxygen isotopes are consumed but regenerate as the cycle loops, acting as catalysts converting hydrogen into helium. This chart compares the energy output of the pp and CNO processes. At lower stellar temperatures, the pp chain is more efficient, but as temperature increases, CNO output rises sharply, surpassing the pp chain above 17 million Kelvin. The theoretical mechanics of the CNO cycle were first established through calculations published by physicist Hans Bethe in 1939. It took over 8 decades to verify those calculations observationally. In 2020, the Borac-CNO collaboration successfully isolated the specific energy spectrum of neutrinos produced by the CNO cycle. The detection confirmed the proposed magnitude of the cycle, proving that roughly 1.7% of the sun's helium is synthesized via the CNO process. Because neutrinos stream out of the core at nearly the speed of light without interacting with the dense plasma, they provide a real-time data feed. This signal offers validation of the theoretical nucleosynthesis models formulated decades ago. By combining the interior mapping from helioseismology with the chemical data from neutrino flux, astrophysicists construct the standard solar model. This framework links the rigid neutrino-emitting core, the tachocline boundary layer, and the convective envelope driving the surface acoustic waves. Finalizing this model required the uninterrupted diagnostic data provided by orbital observatories like the SOHO spacecraft, which monitors solar oscillations free from atmospheric interference. But building this unified model exposed a problem. When early detectors attempted to capture the solar neutrinos predicted by the standard solar model, they observed only a fraction of the expected flux. This discrepancy created a major interdisciplinary tension. Either astrophysicists had miscalculated the temperature and pressure of the solar core, or particle physicists had misunderstood the nature of the neutrino itself. The acoustic data provided by helioseismology was so robust that astrophysicists could prove their interior temperature calculations were correct. The solar model held, which forced the paradox entirely onto the field of particle physics. With the internal mechanics of the sun supported by acoustic data, there was only one logical explanation remaining for the missing particles. The solution was neutrino oscillation. The particles were not missing. They were changing flavors during their journey from the sun's core to detectors on Earth. This conclusion forced a revision of existing theory. In order for neutrinos to oscillate between flavors, they must possess mass, a property that contradicted the accepted standard model of particle physics at the time. The experimental proof that neutrinos have mass demonstrated that previous models of subatomic matter were incomplete, recognized with the 2015 Nobel Prize in Physics. The incredible diagnostic challenge began with an environment so optically opaque that light is completely trapped for 170,000 years. We mapped this stellar engine by listening to its deep acoustic resonances and catching the particles passing through its dense plasma. Quantifying the mechanical state of the solar core provided the evidence necessary to prove that neutrinos possess mass, a discovery that necessitated a revision of the standard model of particle physics.